In this lesson, we want to talk about powers and roots of complex numbers. All right, so in the last lesson, we talked about multiplying two complex numbers together when they're in polar form using something called the product theorem. So what we're going to do here is just go a step further and we'll talk about these powers and roots of complex numbers. So what I'm going to do is I'm just going to start out with a simple complex number, something generic in polar form. So I'm just going to write r times the quantity cosine of theta plus I times the sine of theta, okay? So remember, when we talk about r, that's the absolute value of the complex number. When we talk about theta, it's referred to as an argument, okay? If you think about the complex number as a vector, it's going to be the direction angle, okay? So let's say that I wanted to raise this to, let's say, the second power, right? So I'm squaring this, and basically what I would do here, I would just expand this, right? So this would be r times the quantity of the cosine of theta plus I times the sine of theta, okay? And I'm going to multiply by itself. So r times the quantity of the cosine of theta plus I times the sine of theta. So you can see here that you have r times r. Remember, you're multiplying the absolute values together. So this gives me r squared. Notice that this guy right here, this exponent here on r, matches this exponent here, okay? So this is going to be important. Then times the quantity, you have cosine of, remember, you add the arguments. So theta plus theta is 2 theta. Then plus I times the sine of theta plus theta. You add the arguments. This is 2 theta. So I want you to notice some things. Again, this 2 here, this exponent matches this exponent here. And then this guy here inside the parentheses, it's multiplying the argument. So the general rule is whatever this exponent is, and this can be any real number. For today, we're just going to work with positive integers. But whatever this guy is, it's going to basically be your exponent on r, and then it's going to be multiplied by your argument inside the parentheses, okay? Now, I can do another one with you just to show you this. So let's say we did something like r times the quantity cosine of theta plus I times the sine of theta, okay? Let's say now we cube this guy, okay? So we know that this would be equal to basically this guy times another one, okay? This guy times this guy would give me this guy. So I can go ahead and write r squared times the quantity cosine of 2 theta plus I times the sine of 2 theta, okay? Then multiplied by one more of these. So r times the quantity cosine of theta plus I times the sine of theta, okay? So what is this going to give me? Again, r squared times r is going to be r cubed, so r cubed. Again, notice this exponent here matches this exponent here, okay? So basically after that, inside the parentheses, you're going to have the cosine of 2 theta plus theta is going to be 3 theta, okay? Plus I times the sine of 2 theta plus theta is 3 theta. So again, this exponent here of 3 is going to be your exponent here on r, and then inside the parentheses is going to be multiplying your argument. Okay, and this should make sense because if I'm raising this to the third power or I'm cubing this, then basically I have 3 of these. So I have 1, 2, and then a third one, right? So it makes sense that I have 1, 2, 3 r's. So it's going to be r cubed, right? R times r times r. And then you have this one, and another one. So if you're adding the arguments, you have theta plus theta plus theta, which is 3 theta, okay? So that's what's going to work. If you raise this to the 4th power, you see the same thing, 5th power, 6th power, whatever you want to do, any real number. Okay, so formally, this is our theorem here. You can write this down for your notes. Basically, if you have some complex number in polar form, so let's say r times the quantity cosine of theta plus I times the sine of theta, and this is raised to some real number n, okay, again, we're going to use just positive integers today, then basically you can say it's r to the power of n times the quantity, you have cosine of n times theta plus I times sine of n times theta, okay? So this n is going to be multiplying your argument, and it's also going to be your exponent on r, or the absolute value of that complex number. Again, for the shorthand, remember this is the c, the I, the s. That's where this abbreviation comes from. So we have r to the power of n, and then you have this cis, the cis, some people say, and then we have n times theta. All right, let's jump in and look at an example. So we're going to start with something very, very easy. So we have the negative of 5 times square root of 3 over 2 plus 5 halves I, and this whole thing is being squared. Now, obviously this is in rectangular form, and since this is just being squared, you could expand this and just perform the operation that way. But what we're going to do is use our little theorem. So we're going to first write this in polar form, then we'll use the theorem, okay? So I'll say this is equal to, I'm going to put my r times the quantity cosine of theta plus I times the sine of theta, okay? And this is going to be squared. okay? So I'm going to fill out my r and my theta. So to get those, remember, your r, okay, which is the absolute value of the complex number, is the square root of, you're going to take your real part, which is the negative of 5 times square root of 3 over 2, and you're going to square this, and then plus you're going to take your imaginary part, which is 5 over 2, okay, and you're going to square this. So let me scroll down and get some room going, and we'll come back up in a minute. Basically, if I have negative 5 times square root of 3 over 2 squared, the negative 5 squared is 25. The square root of 3 squared is 3. 2 squared is 4. So this is 75 over 4. So let's just replace this and put 75 over 4. And that is a terrible 5, so let's fix that. And then the 5 halves squared is just 25 fourths. So let's put plus 25 fourths. Now, 75 plus 25 is 100, and 100 divided by 4 is 25, okay? And obviously, 25 is a perfect square. Square root of 25 is 5. Okay, so let's say this is 5. Now, let me come up here just a little bit. So let me scroll up just a little bit. And I'm going to erase this r, and I'm going to put a 5 in there for the actual value. And now I need to figure out what theta is. So lots of ways to think about this. Remember, your tangent of theta, if you're thinking about this as x plus yi, well, it's going to be y over x, okay? If you're thinking about this as a plus bi, then it's b over a. It's the imaginary part over the real part, okay? But you have to be careful about this because when you use your inverse tangent function, you're only going to get something in quadrant 1 if this guy's positive, and something in quadrant 4 rotating clockwise if this guy's negative, okay? So you got to be real careful here. So let's come up and think a little bit about this. So the y part is 5 halves, okay? So that's 5 halves. Then I'm dividing by a fraction, so I'm going to multiply by the reciprocal. The x part, or the real part, is going to be the negative of 5 times square root of 3 over 2. I'm going to flip that, so I'm going to put 2 over 5 times square root of 3. Okay, I'm dividing fractions, that's why I did that. Okay, so what I would see here is that this would cancel with this, and this would cancel with this, so I have the negative of 1 over the square root of 3. Rationalize the denominator, this is square root of 3 over square root of 3. And so this gives me the negative of, you have the square root of 3 over 3, okay? So let's think about this for a moment. If I type this into my calculator, okay, as the inverse tangent of this guy, I'm going to get something in quadrant 4, and I'm also going to get a negative angle, okay? So it's going to rotate clockwise. That is not what I want, okay? So what I'm going to actually do is I'm going to do the inverse tangent of, I'm just going to make this positive, so square root of 3 over 3. This is going to give me my reference angle, okay? So if I punch this into the calculator, I get pi over 6, okay, if you want to work with radians, or you get 30 degrees if you want to work with degrees. Now, this is not my answer because I'm not in quadrant 1. Okay, let's get rid of this. We don't even need this anymore, okay? Let's think about where we are. If you were to graph this complex number on the complex plane, then basically you think about the fact that this is negative, so the real part's negative, and this is positive, right? So this is positive. So from the origin, I would go to the left and I would go up. That puts my complex number in quadrant 2, okay? So in quadrant 2, I want an angle with a reference angle of pi over 6 or 30 degrees, okay? So basically you can say theta is equal to, you could do pi minus your pi over 6, okay? And I can do 6 pi over 6 to get a common denominator. So this is 5 pi over 6, which is 150 degrees, right? If you wanted to do this with degrees, you do 180 degrees minus 30 degrees. So again, it's 150 degrees. So let's do 5 pi over 6. So 5 pi over 6. So that's the tedious part. So let's just erase this and this and go 5 pi over 6. Of course, you can put 150 degrees in there if you feel more comfortable with that. That's up to you. Okay, so now that we have this done, finding our result here is really easy, right? Using our little theorem, this r value here is raised to this power. So 5 is squared. 5 squared is 25. That's easy. Then times the quantity, the cosine of, this gets multiplied by this exponent. So we'll have, let me do this in a different color, 2 times 5 pi over 6, okay? Then plus, let me return to this other color, so plus your I times the sine of, again, it's going to be 2 times 5 pi over 6, okay? That's all it is. It's very, very simple. Most of the work is just putting it in polar form. So once we have this, we can think about, okay, well, this would cancel with this and give me a 3. This would cancel with this and give me a 3. So this is going to be 25 times the quantity. You have your cosine of 5 pi over 3, okay, plus I times the sine of 5 pi over 3, okay? And 5 pi over 3 is 300 degrees if you want to write it like that. Again, up to you. Now, this is the answer in polar form. If you want to put it in rectangular form, again, it's all over the place in terms of what your teacher would ask for. Let's just get a little quick practice with that. So the cosine of 5 pi over 3, again, the reference angle there is pi over 3, okay, or 60 degrees. So the cosine of pi over 3 is going to be a half, right? And cosine in quadrant 4 is going to be positive. So this equals 1/2. Now the sine of 5 pi over 3, again, pi over 3, if you think about the sine of pi over 3, well, that's going to be square root of 3 over 2, but we're in quadrant 4, so sine is negative, so this is the negative of the square root of 3 over 2, okay? So let's go ahead and replace these. I'll go ahead and say this is equal to 25 times, I'll say this is 1/2, so this is going to be 1/2, and then plus, you have I multiplied by, this is going to be the negative of the square root of 3 over 2. Probably better to kind of switch this around here and then maybe scooch this down a little bit for formatting. And let's close this down, okay? So let's go ahead and distribute this 25 in. So this would be 25 over 2. And then basically I have plus negative here. Might as well just write minus. It's a little bit easier. I'll say minus 25 times square root of 3 over 2. Now you can put your I out here, and then sometimes people put the I there. It's really up to you. It's very clear here that it's not under the square root symbol, so I would just leave it like this. So this would be your answer in rectangular form, your 25 over 2 minus 25 times square root of 3 over 2, and then times I. All right, let's look at another example. So this one I'm going to give it to you in polar form, make it a little bit quicker. So we have 2 multiplied by the quantity cosine of 7 pi over 4 plus I times the sine of 7 pi over 4. And this whole thing is raised to the 5th power, okay? So if it's in polar form already, it's super easy, right? This R value here, this 2, is going to be raised to the 5th power. So you have 2 to the 5th power. We know that's 32, but we'll just simplify that in a moment. Then inside the parentheses, you'll have your cosine of, again, this exponent here of 5 is going to be multiplied by the argument. So 5 times 7 pi over 4, okay? Maybe make these parentheses a little bit bigger. Then we'll go plus I times the sine of 5 multiplied by the 7 pi over 4. Let me close the parentheses there. So we'll say this is equal to, let's go ahead and say this is 32, right? 2 to the 5th power. Then times the quantity. 5 times 7 is 35. So this would be the cosine of, we'll say, let me make that S a little bit better. So we'll say this is 35 pi over 4. And then we'll say plus I, so plus I, times the sine of 35 pi over 4. Now again, some teachers don't care. You can leave this as your answer if they say we want it in polar form. That's really up to you. If you need to put it in rectangular form, it's kind of hard to do that with 35 pi over 4. I mean, I know we can use calculators, but if you wanted to think about this off the unit circle, for myself, I always like to put it between 0 and 2 pi, with 0 included and 2 pi not, okay? So if you think about 35 over 4, forget about the pi for a second, 35 over 4, that's really close to 36 over 4. 36 over 4 is 9, okay? So that tells me if I think about 2 pi, 4 pi, 6 pi, 8 pi, okay, I would want to subtract 8 pi off to get myself a coterminal angle. So if I did 35 pi over 4 minus 8 pi, of course I could write this as 32 pi over 4, 32 pi over 4, this is 3 pi over 4. Okay, so that looks a little bit easier to work with, so I'm just going to change this. Again, some teachers require it, some don't care. So 32 times the quantity cosine of 3 pi over 4. Let me make that a little bit better, okay? Then plus I times the sine of 3 pi over 4. Okay, so that's done. So if you want your answer in polar form, again, this one if your teacher doesn't care, this one if they do, okay? If you want your answer in rectangular form, well then again, I've got to go through and figure out, well, what is cosine of 3 pi over 4? And what is sine of 3 pi over 4? So if you're not used to working with radians, if you haven't memorized your unit circle, this is 135 degrees. So you know this is in quadrant 2. So sine is positive, okay? And this guy is negative. And remember, with 135 degrees, you have a 45-degree reference angle, or in terms of radians, it's pi over 4, okay? So for both of those, it's square root of 2 over 2 if you think about pi over 4, right? But this one's negative and this one's positive. So this would be the negative of the square root of 2 over 2. And this would be positive square root of 2 over 2, okay? So we would say that you have equals, I'll go 32 times the quantity. I'd have the negative of the square root of 2 over 2. And then plus, you'll have your square root of 2 over 2 times I. Okay, again, the I gets changed around based on what book you're looking at, what teacher you're working with. Sometimes they put it out in front there. It's really up to you. So what I'm going to do here is just say that 32 is multiplied by this. 32 divided by 2 is 16. So this would be negative 16 times square root of 2. Okay, plus 32 times this. The 32 divided by 2 is 16. So I'm going to say 16 times square root of 2 and then times I. Now again, this is all over the place in terms of how the formatting goes. Typically with this, you'll see 16I and then times the square root of 2. Again, you don't want to think that it's underneath this square root symbol, so that's why this is done, okay? So this would be your answer in polar form right here, okay? And then in rectangular form, we say negative 16 times square root of 2 plus 16I times square root of 2. All right, so now let's talk about the roots of complex numbers. So I'm going to use this first example here to derive a little formula we can use. If you don't want to watch it because it's a bit tedious, you can just skip ahead to where we're doing the examples. So first and foremost, every non-zero complex number is going to have exactly n distinct complex nth roots. So you might read this in your book and think, what in the world does that mean? Well, what it means is that every given non-zero complex number is going to have exactly 2 square roots, 3 cube roots, 4 fourth roots, 5 fifth roots, so on and so forth. So what we can do is use this example here to come up with a little formula, okay? Let's say that I asked you to find the 3 complex cube roots of this number, okay? What does that mean? Well, let's just go back to regular numbers. Let's say I had just the number 8, okay? So the number 8. What if I wanted to find the cube root of that? Well, I'm looking for a number that when cubed gives me this number, okay? So we know this is 2, right? So 2 cubed gives me 8. So I'm going to do the same thing. I'm going to be looking for a number that when cubed produces this number here, okay? So all I'm going to do, let me just rewrite this. So I'll just say that 3 times the quantity cosine of, let's say, 45 degrees plus the I times the sine of 45 degrees is going to be equal to, again, I'm just going to take a generic complex number in polar form. So I'm going to say R times the quantity cosine of, I'm going to use alpha here instead of theta. So plus, I'll do I times the sine of, again, I'm going to use this alpha, okay? So now I'm just going to raise this to the third power. There is nothing different between this and what I just showed you with 8 being equal to 2 cubed, okay? I'm just taking this number, raising it to the third power. So this number right here is going to be a cube root, okay, of this number because raising it to the third power produces this. Just like 2 is a cube root of 8 because 2 to the third power is 8, okay? It's all it is. So from this point on, what I'm going to do is just simplify things and come up with a little formula, okay? So I'm just going to say 3 times the quantity cosine of 45 degrees plus I times sine of 45 degrees, okay, is equal to, if I use my theorem from earlier, R would be cubed, so R cubed, and then times the quantity cosine of, I'm multiplying the 3 by the argument, so 3 times my alpha there, plus I times the sine of 3 times alpha, okay? So in order for this to be true, you've got to think about the parts of this equation. So this would have to be equal to this, okay? And then this would have to be equal to this, and then this would have to be equal to this, okay? So in other words, R cubed would have to be equal to 3, which tells me if I take the cube root of each side, okay, the cube root of each side, that R is going to be equal to the cube root of 3, okay? And we'll see this in our little formula in a moment. For right now, this is what we have, okay? So let me bring this up here so that's out of the way. And then the next piece would be that the cosine of 45 degrees is equal to the cosine of 3 times alpha, okay? And then also the sine of 45 degrees is equal to the sine of 3 alpha, okay? So let's think about this for a moment. We know about coterminal angles, okay? And we know that, let's say the cosine of 45 degrees has the same value as the cosine of, if I added 360 degrees to that. So if I said the cosine of 405 degrees, this would be equal to the cosine of 45 degrees. And you can pause the video and punch into your calculator. You should know that those are equal. It's also equal to the cosine of a negative 315 degrees, okay, if you wanted to do it that way. Okay, so knowing this fact, what we could do is set 3 times alpha, so 3 times alpha, equal to this 45 degrees, okay, plus I'm going to do 360 degrees times some integer k, okay? Now, we don't have to consider negatives. I'm going to show you how solutions just keep repeating themselves. I'm just going to work with 0, 1, and 2, okay? And I'll show you that when you get to 3, 4, 5, 6, things repeat. Also, if you go -1, -2, -3, you're just getting repeat solutions, okay? So what I would do here is I would simplify this a little bit, and I would divide both sides by 3. Okay, so both sides by 3. So I'd have that alpha is equal to 45 degrees divided by 3 is 15 degrees, okay? Then plus 360 degrees divided by 3 is 120 degrees, and then times k, okay? So to get the values for alpha, you're going to see in our little formula, you plug in, if I'm trying to find the cube root, then I'm going to plug in 0, 1, and 2, okay? So I start with 0, then I go to 1, then I go to 2. If I was trying to find the fourth root, I would go 0, 1, 2, 3. So it's always 1 less than that number. Okay, so if it's 4, you're going to 3. If it's 5, you're going to 4. If it's 6, you're going to 5, so on and so forth. So let's go ahead and go through and say our first alpha would be 15 degrees plus 120 degrees times 0. So 120 degrees times 0. So this is basically going to be 15 degrees. Then another alpha would be 15 degrees plus 120 degrees times 1. So this is going to be 135 degrees. So 135 degrees. Then our other alpha is going to be 15 degrees, plus you're going to do 120 degrees times 2, and this is going to give me 255 degrees, okay? And then again, we don't need this, but if you did go to 3, so alpha is equal to 15 degrees plus 120 degrees times 3, well, this is 360 degrees, plus 15 is 375 degrees. 375 degrees and 15 degrees are coterminal angles, okay? So if I was to say the cosine of 15 degrees or the cosine of 375 degrees, it's the same, okay? So you don't need to go 3 and 4 and 5 and 6. You're just going to get repeat solutions, okay? So you don't need that. You also don't need to do the negatives because you're just going to get repeat solutions. So let me erase this. So coming back now, let me show you that these solutions work, okay? So let me box this off. Remember, originally we were looking for the 3 cube roots. So the 3 numbers that I could plug in here and cube them and get back to this number. So let me show you with the first solution for alpha. So we have our r value, which is the cube root, okay, of 3. And then it's multiplied by the quantity cosine of alpha. So one of those would be 15 degrees plus I times the sine of 15 degrees, okay? Let me get rid of this one. Then the next one would be the cube root of 3 times the cosine of, it would be 135 degrees, plus I times the sine of 135 degrees, okay? Let's get rid of this one. And then your last root here, so the last cube root, would be the cube root of 3 times the quantity, the cosine of 255 degrees, plus I times the sine of 255 degrees, okay? So let's get rid of this. Now, if you were to cube each one of these, you're going to get back to this right here. And we can just do it mentally. We don't need to actually go through it. If we cube this number here, again, following that theorem from earlier, this guy right here would be cubed. So cubing the cube root of 3 gives me 3. So it gives me back that number. Then if I multiply 3 times 15 degrees, I get 45 degrees. If I multiply 3 times 15 degrees, I get 45 degrees. So you can see that cubing this first one right here gives us this back. Now, I'll let you do this one and this one on your own. Just cube them. You're going to see that the angle you get in each case is going to be coterminal with this angle here that's 45 degrees. In this case, it would be 405 degrees. And in this case, it would be 765 degrees. Okay, so let's go from our example and make a nice little formula. So if n is any positive integer, and r is a positive real number, and theta is in degrees, then the non-zero complex number, let's say r times the quantity cosine of theta plus I times the sine of theta, is going to have exactly n distinct nth roots given by the following. So we're going to say that we have the nth root, okay, of this r. You saw earlier we were looking for cube roots, so we had the cube root, which was n was 3, of, in our case, it was 3, so it was the cube root of 3, okay? And basically, we're going to multiply this by the quantity. You'll have the cosine of alpha plus I times the sine of alpha, okay? And basically, what alpha is going to be, I'll do degrees first and then I'll do radians. So alpha is going to be theta, okay, so this guy right here, divided by your n. Okay, so you saw earlier, what we had was 45 degrees divided by 3, which gave us 15 degrees, okay? Then plus, you're going to do 360 degrees times k is just some integer, and I'll talk more about that in a second, divided by n. So in our example, you saw 360 degrees divided by 3, okay, which gave us 120 degrees. And then multiplied by k, where basically k is going to be equal to 0, 1, 2, 3. We'll put the 3 dots here to show the pattern continues, and then we'll go n minus 1, okay? So in our case, our n was 3, so we went 0, 1, 2. Then 3 would give us a repeat solution, so would 4, so would 5, so would 6, so on and so forth. Now, if you're working with radians, then you would adjust this formula, and basically instead of 360 degrees, you would just put 2 pi in there, okay, in terms of radians. Nothing else is going to change. So just depending on if you're working with degrees or radians, you would either want to use 360 degrees for degrees or 2 pi for radians. All right, let's go ahead and look at an example. So we want to find all nth roots, okay, and we're going to write our answer in polar form. So we see that n is set equal to 4, so we want to find the 4 fourth roots, okay? So I'm going to start by writing this guy right here, this negative 3 times square root of 3 minus 3i in our polar form, okay? And so let's go ahead and say that the r value would be what? The square root of, we take the negative of 3 times square root of 3, we're going to be squaring that, plus you're going to take your negative 3, okay, we're going to be squaring that. So the r is going to be equal to, we'll say the square root of, negative 3 squared is 9, square root of 3 squared is 3, 9 times 3 is 27. So this is 27 plus negative 3 being squared is 9, 27 plus 9 is 36, so r equals the square root of 36, so r equals 6, okay? So we've got that part down. Let me go ahead and say that in polar form, this negative 3 times square root of 3 minus 3i would be equal to, I'd put a 6 there, times, you're going to have your cosine, okay, your cosine of theta, I'll replace this in a second, plus your I times your sine of theta, okay? So for theta, again, remember that the tangent of theta is equal to, take the imaginary part, so negative 3, over your real part, which is negative 3 times square root of 3. And so with this, we see the negatives are going to cancel, the 3's are going to cancel. So you have 1 over square root of 3. Again, rationalize the denominator, so square root of 3 over square root of 3. So this is going to be what? Square root of 3 over 3. So if I did my inverse tangent, so my inverse tangent here of square root of 3 over 3, let me make that 3 a little bit better. If we punch this into our calculator, you're going to get 30 degrees, or pi over 6 if you want to work with radians. Let's just work with degrees. So I'm going to say this is 30 degrees. So this is my reference angle. So let me erase this. And let's think about where this complex number would be if we graphed it. So this is negative, and so is this, right? So I have a negative real part and a negative imaginary part. So from the origin, I would go to the left, and then I would go down, okay? So that means I'm going to be in quadrant 3. So my theta here would be 180 degrees plus the reference angle of 30 degrees, which is 210 degrees, okay? So I can just erase this, and I'll go ahead and put 210 degrees there. So 210 degrees. Once you have this in polar form, it's just a matter of plugging into your formula. You want to do your nth root of r. So in our case, n is 4 and r is 6. So we want the fourth root of 6. So we want the fourth root of 6. And you're going to have 4 of these, but I'm just going to start out with the first one, okay? Inside of here, what are we going to have? We're going to have the cosine of, again, we call this alpha plus I times the sine of alpha, okay? And alpha, since we're working with degrees, alpha is going to be equal to, you have your theta divided by n. In this case, the n is 4. Plug that in a second. Plus, you have your 360 degrees divided by n times k, where we say that k is equal to, in this case, because it's 4, it's going to be 0, 1, 2, and 3. Okay? So you just go up to 1 less than whatever n is. That's all it is. So in our case, let's just plug this in. So n is going to be 4. So let's erase this and put 4 in each case, okay? And then theta is coming from here. So it's 210 degrees, okay? So let's put 210 degrees here. So if I divide 210 degrees by 4, it's going to give me 52.5 degrees. So 52.5 degrees. And then 360 degrees divided by 4 is going to give me 90 degrees, okay? So 90 degrees. So basically, to set this up, the first one would be, again, if this guy was 0, plug that in, this is gone. So you just get 52.5 degrees. Okay, so you can put that in there. So 52.5 and 52.5. Now, you can pause the video and you can raise this to the 4th power, and you'll see that you get back to this guy right here. Okay, and then, of course, you can convert that back into rectangular form if you wanted to get back to that original form we started with. Okay, but let's go ahead and keep going. And basically, let me drag this down just a little bit. And I'm going to slide my screen just a little bit down, okay? And basically, now I'm going to do the fourth root of 6 times the quantity. I'll do the cosine of, and then I'll leave that blank for now, and then I times the sine of. And let me leave that blank for right now. So the next one would be, this guy would be 1 now. Okay, so I'm going to plug in a 1. So basically, 90 degrees times 1 is 90 degrees, and 90 degrees plus 52.5 degrees is going to be 142.5 degrees. And I forgot my degree symbol here and here, so let me put that in. So 142.5 degrees. Let me make that decimal point a little bit better. So from here, all I'm going to do is add on 90 degrees, okay, 2 more times. So I can just get rid of this, okay, once you understand the pattern. And basically, I can just copy this. And so 142.5 plus 90 is 232.5. So this would be 232.5 degrees. And this would be, again, 232.5 degrees. And then add 90 degrees again, and you get 322.5. So 322.5 and 322.5, okay? So this would be your 4 fourth roots for that number. I'm leaving these in polar form. All right, let's take a look at another example. I think this is going to be pretty easy for us at this point, but I want to throw something in here. Sometimes your book will ask you to graph the roots on the Argand diagram or the complex plane. So let's go ahead and do this. So we have -8 plus 8i times square root of 3. Again, n is going to be 4. So I'm looking for the 4 fourth roots. Now, again, this is given to us in rectangular form, so I need to convert it into polar form first, okay? So the r value times, again, the quantity cosine of theta plus I times the sine of theta. So let's do this quickly. So r is going to be what? The square root of -8 squared is 64. And then if you have 8 times square root of 3 being squared, it's 64 times 3, which is 192. Okay, so you're adding those two together. And that's going to give me 256. If I took the square root of that, I would get 16. Okay, so let's just erase this and put 16 here. Then for theta, it's going to be where? The real part is negative, so I'm going to the left. The imaginary part is positive, so then I'm going up. So from the origin, if I go to the left and I go up, I'm going to be in quadrant 2. Okay? So let's say that theta will be equal to 180 degrees minus my reference angle. And the reference angle here, let's go 8 times square root of 3. And I'm going to divide that by, forget about the negative, let's just do 8. This is going to cancel with this, so this is square root of 3. Okay, so I'm going to say the tangent inverse of this guy right here is going to give me 60 degrees, okay? So if I subtract 60 degrees away from 180 degrees, okay, because this is my reference angle in quadrant 2, well, it's going to be 120 degrees, okay? So that's my theta. Let's get rid of this. Let's put in 120 degrees and 120 degrees. Okay, so that's pretty quick. All right, so from here, I need to get the 4 fourth roots. So in each case, I'm going to take the 4th root of 16, right? Because again, it's the nth root of r. So n is 4, r is 16. So the 4th root of 16 is 2, right? Because 2 to the 4th power is 16. So I'm going to put 2, 2, 2, and 2, okay? Let's go ahead and set this up in each way. So cosine, 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 and then cosine, okay? So what's going to go here, 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 and here? Remember, when you think about the formula, if you call this alpha, it's equal to, again, you take theta, okay, which in this case is 120 degrees, and you divide it by n. So you divide it by 4. So in this case, that would be 30 degrees, okay? Then plus you have your 360 degrees times your integer k divided by your n. So 360 degrees divided by, in this case, it would be 4, would be 90 degrees, okay? So this would be 90 degrees times k. So for the first instance, this would be 30 degrees. So let's go ahead and put 30 degrees here. I'll fill out the rest in a moment, okay? In the next instance, it's going to be plus 90 degrees. So this would be 120 degrees. Then plus 90 degrees. So this would be 210 degrees. Then plus 90 degrees. So this would be 300 degrees. So let's get rid of this. And let's put our plus, 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 I, and I. And then the sine, the sine, the sine, and then the sine of 30 degrees, close that down, and this will be 120 degrees, close that down, and then 210 degrees, close that down, and then 300 degrees, okay? So these are our 4 fourth roots, okay, for this number in polar form. Okay, so how would we go about graphing these complex roots? Well, basically, each of these can be represented as a position vector in the complex plane. So notice that your magnitude in each case is 2. Okay, so 2, 2, 2, and 2. So what you could do to represent that is you could have a little circle with the center at the origin and where the radius is 2. Okay, so each one of these as a vector is going to have an initial point at the origin and a terminal point that's going to touch that circle that you drew. Okay, and then in terms of the direction angle for the vector, you just get it from here. So the first one would be 30 degrees, the second would be 120 degrees, the third one would be 210 degrees, and the fourth one would be 300 degrees, okay? So these guys are going to be spaced 90 degrees apart, okay? So equally spaced 90 degrees apart. So if we go to our little coordinate plane, and I know that most people put imaginary here, so you can put that if you want. So you can put imaginary, and then for this, you could put real. But again, if you write this as x plus yi, then x could still be your real axis, and y could be your imaginary axis. It's really up to you or your teacher, okay? So I'm just putting it this way. So when we think about this, again, the first solution was 2 times the quantity of the cosine of 30 degrees plus I times the sine of 30 degrees. We abbreviated it here. But you can see that I have a position vector. The initial point is at the origin. The terminal point is going to touch this little circle that I drew, okay, with a radius of 2 and a center at the origin, okay? So you see that this is a 30-degree angle, okay? And then if we go another 90 degrees here, so this is another 90 degrees, you can see that little 90-degree symbol there. Basically, I'm going to get to my next solution. So the angle here is 120 degrees. Again, if I started here, 30 degrees plus 90 degrees gives me 120 degrees, okay, for the whole thing. And then basically, you can see that it touches, again, our little circle. If we keep going around, this is another 90 degrees, and then this is another 90 degrees. Okay, so it keeps putting you to another solution. So this angle here, if I started here and went all the way to here, this is 210 degrees. If I started here and went all the way around to here, this is going to be 300 degrees. Okay, so that's basically how you can sketch the graph if you're given this as an assignment. Again, just take your magnitude, okay, in each case, ours was 2, and draw yourself a little circle with the center at the origin and the radius of that number. Okay, in our case, it's 2. Then what you want to do is have position vectors. So they start at the origin, and their terminal point is going to be on that circle, and your direction angle in each case is given by the angle. So here it's 30 degrees, here's 120 degrees, here it's 210 degrees, and here it's 300 degrees. All right, so let's wrap up the lesson and look at another example. Here we're going to be solving a simple equation using the roots of a complex number. Okay, let's say we saw something like x cubed minus 27, and this was equal to 0. The first thing, we know that since this polynomial here is of degree 3, okay, we have this exponent of 3 here and none higher, well, we know we're going to have exactly 3 complex solutions for this equation. Okay, that's the fundamental theorem of algebra. So how could we use the roots of a complex number to solve an equation like this? Well, the first thing is I could add 27 to both sides, okay? And I could set this up and say, really, this is x cubed is equal to 27. Okay, let's pause and think about this for a minute. I am looking for a value that I can plug in here and cube it and get 27. So in other words, what number cubed gives me 27? So if I found the 3 complex cube roots of 27, I could plug them in for x, and I would have a true statement, okay? So you might be thinking, well, 27 is a real number. Remember, all real numbers are complex numbers. The real number system is a subset of the complex number system. I can write 27 as 27 plus 0i, okay? So with this format here, I can also write this in polar form. This is really easy to do. If you think about the r value, it's just going to be 27, okay? Because you think about this as, okay, well, r is equal to the square root of 27 squared plus 0 squared. 0 squared, you can just get rid of that, okay? And the square root of 27 squared is just 27. So our r value is 27. Then, in terms of this inside part, it's easy as well. So you'd have the cosine of, again, theta plus I times the sine of theta. So you don't need to do any inverse tangent function here or anything like that. Just think about this complex number if you graphed it on the complex plane. You would simply start at the origin and go 27 units to the right, okay? So there's no movement at all vertically, right? You're on the x-axis or the real axis if you want to think about it that way. So really, this is going to be a 0-degree angle, right? I haven't moved off the real axis. So I'll just go ahead and put this as a 0-degree angle. Okay, and that's all it is. So this is me writing the number 27, first in rectangular form, and then in polar form. Now, in order to find my 3 complex cube roots, I'm going to start with my simple little formula. So I have the nth root of r. So in this case, n is 3, right, because I'm looking for a cube root, and r is 27. Well, the cube root of 27 is 3, right? 3 times 3 is 9. 9 times 3 is 27. Okay, so I can set this up. I know I have 3 of them, so I'll go 3, I'll go 3, and I'll go 3. Okay, let me just write all this out. So we have cosine, cosine, and cosine, and we're going to use alpha. We're going to use alpha, and alpha, and I'll replace this in a moment. So plus, plus, and plus, I, and then sine, sine, and sine. Okay, and I'm going to use alpha again, and alpha again. Okay, so again, these are all going to change based on that input for k. So to find alpha, let's go ahead and set this up over here, put a little border here. To find alpha, the idea is that it's theta, whatever this is, in this case it's 0 degrees, divided by n, which in this case is 3, okay? So 0 degrees divided by 3 is just 0 degrees. So this is 0 degrees. You can put it there or leave it off. It doesn't matter. It's not going to change anything. I'm just going to leave it for the sake of completeness. So then plus, you have 360 degrees divided by n. In this case, that's 3. So this is 120 degrees, okay? And then times your k. Now, k is going to be 0, 1, and 2. Basically, your pattern is what? It's 0, 1, 2, 3, n minus 1. Let me put a comma in there to make that complete. And basically, you have 3, so 3 minus 1 is 2. So in this case, we would only go up to 2. Okay, so that's how that works. So I'd start with a 0 there. And of course, 0 degrees plus 0 degrees is just 0 degrees. So the first guy here is just going to be 0 degrees. So I can put that in here, and that should make sense. If I cubed this, 3 cubed would be 27, and then you would basically have 3 times 0 degrees, which is still 0 degrees, and 3 times 0 degrees, which is still 0 degrees. So in polar form, I would be right back to this here. 27 times the quantity, cosine of 0 degrees, plus I times the sine of 0 degrees, which again in rectangular form is this, and written just as a real number is this, okay? So then the other one, I'm just going to add 120 degrees each time. If I plugged in a 1 there, this would just be 120 degrees. So 120 degrees, 120 degrees. Add another 120 degrees. If I plugged in a 2 there, this would be 240 degrees. So 240 degrees and 240 degrees, okay? So these 3 numbers here in polar form, these 3 complex numbers in polar form, if you cube them, they would each give you 27. Now, typically, if you were in an algebra class, you would not give this as your solutions, right? You would want to convert this back into rectangular form, okay? So how would we do this? The cosine of 0 degrees is going to be 1, and the sine of 0 degrees is going to be 0. So basically, you would have 3 times 1, which is 3. So I would say x is equal to 3. Okay, that would be my first solution. For this one, the cosine of 120 degrees and the sine of 120 degrees, let's think about this. There's a 60-degree reference angle here, 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 and here, right? 120 degrees, 240 degrees, you have a 60-degree reference angle. So the cosine of 60 degrees is going to be 1/2. And the sine of 60 degrees is square root of 3 over 2, okay? So it's just a matter of getting the signs right. Remember, sine is going to be positive in quadrants 1 and 2, and 120 degrees is in quadrant 2. Cosine is going to be positive in quadrants 1 and 4. Okay, so basically cosine is negative in each case because this is quadrant 2, this is quadrant 3, and sine is positive here and negative here, okay? So to get my solutions, let me write this out. I'm just going to scroll down a little bit so we have some room. For this one, I would have what? 3 times, this would be the quantity, negative 1/2, plus this guy is going to be square root of 3 over 2, okay, times I. So if I go ahead and distribute the 3 into each term, I would have negative 3/2, and then plus my 3 times square root of 3 over 2 times I. Okay, so that's another solution. Then the other one, let me just go ahead and keep this as negative, and I'm going to change this to negative now. So basically you would have negative 3/2 again, and then minus the 3 times square root of 3 over 2, and then times I, okay? So I would write this in a more compact form. I would just do plus or minus here and get rid of this. That way you can more cleanly write your 3 solutions. So if you were in an algebra class and they gave you this equation, you would want to give this as a solution. Now in this particular case, this is probably not the fastest method to do this, but it's one such method that you can get a solution. Now let's think about this graphically. If I wanted to show these solutions, again, I'm going to do this in polar form, okay? So on the Argand diagram or the complex plane, again, the magnitude is 3 in each case. So that's the length of your vector. So if you're making a circle, okay, with a radius of 3 that is centered at the origin, each one of these vectors is going to touch that circle, okay? That's going to be your terminal point that lies there, okay? And then your direction angle for your vector is going to be 0 degrees, then the other one's going to be 120 degrees, then the other one's going to be 240 degrees, okay? All of them are position vectors, so they start or their initial point is at the origin. So graphically, this is a rough sketch of this guy. Again, I have a little circle that's drawn, and the radius is 3, and the center is at the origin, okay? Then you have your 3 position vectors. Notice that they're all going to have an initial point at the origin. The terminal point in each case is on that circle, again, where the radius is 3 and the center is at the origin. So your first angle is 0 degrees, okay? It's given by this 3, cis, 0 degrees. Again, this is the abbreviation. The second angle is 120 degrees, okay? So we come from here, we rotate 120 degrees, and now we have that vector there, okay? And the terminal point's there. And then the last one, if I rotate around here, this is going to be a 240 degree angle, okay? So that's how you would sketch the graph of this guy. You'll notice that these guys are equally spaced 120 degrees apart, right? 120 degrees, this is 120 degrees, and this is 120 degrees as well. So this is how you can graph your solutions if you're asked to do them. Again, figure out the magnitude or the length of the vectors. You're going to sketch yourself a little circle, okay, with a radius of that number. In this case, it's 3, and a center at the origin. So all of your vectors are going to be position vectors, initial point at the origin, terminal point's going to be on that circle, and you just get your direction angle from your roots. So we had 0 degrees, 120 degrees, and then 240 degrees.